Now the third topic is completely different than the others, and it involves with a topic which is called homogenization. Although I prepared beforehand to talk to you about growing of film, of thin film, I'll come to it. But as I was thinking this morning about it, I thought there is no point talking about airplanes before we talk about automobiles. So let me start with a very simple example. Suppose you take two kinds of material, two kinds of electric material, one material with conductivity K1 and the second one with conductivity K2. And you put one piece next to another, say in a periodic order. So you have K1, K2, K1, K2, K1 in some fixed interval. Okay, so if U is electric potential of this material, it's what? A, the derivative of U, okay, gradient U, then you take the gradient or the derivative of this in one dimension equal to F. This is second order ordinary differential equation in one dimension in some interval between x0 and x1, and K epsilon, it keeps flipping from K1 to K2, K1 to K2 in a periodic way. So let's write it, and we are asking what happens when this material, it gets to be, this interval gets to be smaller and smaller and smaller. Suppose that we are making such a composite material with 100 million pieces, or let's say with micron size of K1, micron size of K2. So it will be impossible to start to computing in each interval separately. You want to take the whole thing together and in some average sense see to what happens to the electric potential. So what is the limiting of the solution, limit of the solution U sub epsilon when epsilon goes to 0? So a good guess might be that you look at this function K sub epsilon, which is a periodic function of period epsilon. So A of y is one periodic, and you can write it as A of x over epsilon to make the period of size epsilon. And A will take the value plus 1 minus K1 or K2 in each period. Okay, so it's periodic. It has one value and then another value. Same higher value, lower value, higher value, lower value. So in each period it will have two values, the higher and the lower. And you ask, so you look at this function A, which is fast oscillating, A of x over epsilon. You average the A, so this is the average of A. And then the limiting U should satisfy that if you take the average of A, the average of this conductivity, you take the U prime and take the derivative of all this should be equal to F. That seems natural. But that's also the wrong answer. So if you want to solve the limiting problem here, where K epsilon keep flipping, taking the average of K epsilon is the wrong answer. The correct answer is this. You take the average of 1 over A, you get a number, and then you take 1 over this average, and U prime and all this prime. This is the correct answer. So things are not what they seem. If you try to take this material and combine with different conductivities, the limiting one, the effective conductivity is not the average. It's rather 1 over the average. In a sense, you can think of it as the difference between electric current, electric network, which is in parallel or in sequence. In parallel, the resistance, one of the reciprocals, as well as the resistance, is the sum of the reciprocals of the various resistances. And 1 over K is a resistance. So this is an example, simplest example of homogenization that tells you there is a formula there, but it's not the obvious one. And this can be generalized not only to one ordinary differential equation, but to partial differential equations, to systems of equations, and so on. There is a whole theory on homogenizations in hundreds of papers. Okay, now I'll give you a different example, since I'm interested in problems that, number one, come from industry, and number two, they are not in the standard theory. So here is something that came to us from Ford Motor Company. You know that there are various pushers for the development of science. One of them is government regulations. So the government would like that by a certain year, the average car that Ford Motor Company produces, or GM produces, or other companies, will make 30 miles per gallon. And they have to do it, or else they are going to have to pay penalties, heavy penalties. So they begin to think, how can we do that? What do we have to do to get higher mileage? And one possibility is to make materials lighter. Of course, you can drop the bumper, but then you break another government regulation. It says that you have to protect the driver with the bumper, that collision with 5 miles an hour will not damage the car. And by the way, this regulation has been dropped down. No one talks about it, but it's dropped because it's just impossible to make plastic bumpers. You need plastic bumpers basically in order to reduce the weight of the car, but you cannot. But they don't tolerate 5 miles an hour, a little less. So this is out of the window, but it's not talked about much. Okay, so you like to reduce weight, and they make composite materials, like the one I described before. For instance, exchange rods that are used in automobiles used to be made of steel. Now they make them of aluminum, much lighter. But aluminum is breakable, is very brittle. So they reinforce it with carbon particles. So they process a material which is aluminum with carbon. It's a composite. And to this composite, you can apply homogenization. So these are examples where new mathematics is coming out of new models because of government regulations. Now, another area where you can reduce the weight is the gas tank in your car. It used to be made of metals. It's still made of metals in most cars. But Ford Motor Company is beginning to make fuel tank, gas tanks that are made of plastic. Okay, but plastic, you can penetrate. Fuel can get out of plastic. If you have fuel here, it can get out. And there is a government regulation that says that when the car is in a resting position, is parked in your garage overnight, it's not allowed for it to leak more than a certain milligrams of fuel per 12 hours. There is some norms. There are all kinds of regulations. Therefore, a plastic tank is not very good because fuel does permeate through it. A larger proportion is allowed. So what they do, they take fluorine and they coat the inner part by a process which is called blow molding, sort of like that inside, because with a stronger power and hotter stuff. And they fill all the interior with this material, and now it reduces the permeation. But it doesn't do a perfect job. There are little holes everywhere. There's also a big hole where they do the molding, the blow molding. So the question that people asked one of the modelers in Ford was, what is the effect of all these holes? There are lots of them. What's the effect of them? Do they really interfere much with the permeation? So that was the question. So if we denote the density of the fuel in the tank inside by Q0, and that's more or less a constant, and this is the air. This is the air, this is the fuel, and in this little layer, which is maybe 1 millimeter, or maybe 2 millimeters, this is where we are going to study the problem, because that's where the fuel is leaking. It's leaking from density Q0 to density 0 in the air. Once they come to the air, it dissipates, and so it disappears, and density is 0. So Q0 is the density of the fuel in the tank, and C is in this thin layer, and I am now going to draw a picture that will show it more clearly. So, but I'll call Q0 minus C, I call it U. So we are interested in this region here, in this shell-like region. And there are holes here, see? And also parts that don't have holes, of course. And we want to know what is the density of U, what is, actually we want to find what is the derivative of U here, because that means the flux. How much fuel is getting out. So once it gets out, it dissipates. But how much does it get out? It's a derivative of U here. So we want to find the solution of this problem. And here's Laplace U. It's a simple diffusion equation in this region, in this shell. U0 is Q0 down here, because I took Q0 minus C to be the U. So C is 0, and therefore U is Q. If you have a hole, there is a hole here, then the density of the fuel here and inside is the same, because it just goes through. So U here is simply equal to 0. But if you look at the part which has no hole, there is no flux of fuel going through this. So the normal derivative is 0. So in these holes, U is 0. Outside the hole, normal derivative is 0. It's a mixed problem. Neumann in some region, Dirichlet in another region. What happens as the number of holes increase? And it turns out that even that you may have holes that are very total area of the hole, of the small holes, may be very small, maybe even going to 0. Their effect will be tremendous. So the limiting situation is that it's some paper that I wrote with, I think there was another author, I forgot, Yong, Y-O-N-G, is that what you have to look at is not the area of the holes compared to the total area, but this number. Oh, I forgot to mention. Roughly speaking, I don't want to get too precise, the distance between two holes is sigma. Roughly speaking. He actually precisely formulated in terms of distribution of the holes, but roughly is sigma. So if you are in 3 dimensions, n is 2, this is 1, and this is 2, so epsilon square. Sigma is like epsilon square, which means sigma is like sigma epsilon is a radius, and epsilon is the distance between them. Sigma epsilon is the radius of the ball, epsilon is the mutual distance. So if the radius of a ball, of a hole, is approximately like the distance squared, which is very, very small. There is a distance with a very small number, you take the square of it. So if they are more or less proportional, you get some finite number here, then this changes, the condition on this become homogenized, and you get a third boundary value problem with some constant which depends on this beta, which can be written explicitly. This number is actually the capacity of the holes, called the capacity. In 2 dimensions, it's even much, much smaller. It's exponential. So this is what determines the limit. That's another example of a non-standard homogenization that came from the automobile industry. And now I want to come finally to the topic of today, growing films. And this came from Motorola, and of course it has to do with semiconductors. So let me give you a quick introduction about where it comes from. Well, the Bible of Motorola is, in the beginning there was a wafer. And the wafer was made from pulling a crystal, from a crucible, pulling a crystal seed. And that has its own mathematical modeling of fluid mechanics and so on. But I'm just looking finally at the crystal that came out. They saw it in parallel planes, and each of them is called a wafer, and it's a circular, it's a disk of radius or diameter, say 10 centimeters, something like that. They are trying to make them bigger and put more on the chips and so on. So this is a wafer, and they break it into chips, and on each chip they have various patterns, and they come in groups, and in each group there are smaller groups, and so on. There are various orders of magnitude up to a sub-micron. The smallest transistor now manufactured is 0.2 or so micron. This is 10 centimeters. This is this will be, say, a centimeter size. This will be in the, so this is centimeter size. This is 10 to 100 microns. So on. This is finally comes to 10 to the minus 6. So from centimeter, so 10 centimeters is 1 over, it's a 0 point, let's see, it's 10 point, is 0, it's 10 to the minus 1 of a meter to 10 to the minus 6. 5 orders of magnitude. Okay, here is a machine on which the wafers are. Here's a bunch of them, and they go through various processes. So now this, let me describe it, 1 or 2 typical processes. What they want to make from this wafer, they want to divide it into, say, 1 million small transistors, and each transistor is charged or doped indifferently, and it also has a little geometry, which is usually, this is where this will be the home of a transistor. And to create something like this, they are not going to do it with a hammer and anything, because there are no instruments like this. But they are going to cover it with some, or part of it with some photoresist, radiate. The parts where radiation took place becomes harder. The parts that did not become harder, they wash away with some chemicals, and then they put another. Whenever they put a pattern and then they start to put the photoresist, the pattern is done by what's called a mask. So they make a mask, and then they radiate. They make a mask, then they radiate, then they wash away. They make another mask, and it goes on many times, as many as 50 times. Each time they make this process, it may take 2 days. It takes several months to produce a chip. So here is a plasma that they are going to fill in some of the trenches here. Okay, these are atoms that are going around. And the control they have, so this is what this picture shows, the chemical vapor deposition. The position of particular gas, and it probably be just several layers of molecules. And then they stop the process and do something else. They're very, very thin layers. And they have to control it with instruments that are the size of centimeters. They have to control something which is the size of micron. Because it's impossible with such a big thing to control something so small. So this was a chemical vapor deposition. This is another example of what is called rapid thermal processing. Rapid thermal processing. Once vapor landed, they want to make it stick, and they do it by baking it. They can either put it in the oven, same way they make bread, but there are other ways to do it, which are cleaner. And one of them is simply to put some lamps around and raise the temperature in the lamp about 100 degrees per second for about 10 seconds. Keep it there for several seconds and then shut it off. So there is a quartz window through which the light comes, and so there is a gas that came down. Then they put the lamps in, and it's like fusing we had in the previous talk. Try to make it stick by heat. Okay, now they would like to know how, for example, how to deposit so generic question is how to deposit the chemical species on the top in order for the surface of the film that they are growing. See, when they make the semiconductor, it means they are growing a film. They take a silicon substrate and they are growing it layers by layers by layers. So they are growing film. So how to control the flux of a species in order to get a particular surface? That's just a generic question. Okay, and they would like some tools to do this numerically as well. So here is a model problem. For simplicity, we take the Laplace equation. What they actually have is an Navier-Stokes equations away from, this is a wafer. This is a sort of this fast oscillating thing. So for simplicity, we take this. Actually, this is a good approximation near the surface of the chip. Okay, so you want to solve a Laplace equation, boundary conditions on the top. You want to see, okay, and this is fast oscillating, and you want to get an approximate solution. You are not going to solve it with this geometry because, well, you see, each step, let's say, is a micron size. So you have 1 million steps. If you want to do any precise computations, say doing finite elements or finite differences, each difference should be at least small. It should be smaller than each step. Otherwise, you will not get the steps. That means you have to divide it, the region, into at least 1 million. 1 million mesh points along the horizontal direction by 1 million. There will never be a computer. It's dangerous to say there will never be, but I will still say there will never be a computer that can compute with a million by million mesh points. So you're not going to do it this way. You have to do something else. Okay? There is an extra complication here that this boundary is changing during the process. It's again this free boundary business. It's moving. So this boundary here, which I call gamma sub epsilon, say x sub 2 equals epsilon it changes very, the absolute height is very small, but it oscillates a lot. So we don't really know what this is either. Now what is, where is the epsilon appearing here in the data? I mean, why don't I just call epsilon times f epsilon? I can just call it a different letter, and there is no epsilon there at all. I can just call it, say, g of x1 and t. Where is the epsilon? The epsilon comes from this p, and that relates to the deposition. Because the deposition depends very much, because of this photoresist business, it depends very much if you are on the part that received the light or did not receive the light, that it went through the mask or not. So this p is fast oscillating. It's a function of x1 and x1 over epsilon, periodic in this variable of period 1. So for each point x1 here, it's fast oscillating in a periodic way of epsilon size. So this is a model where I have only 2 orders of magnitude, although we can have more orders, 2 orders of magnitude. So the p is the one that is oscillating. Now this is the velocity of the boundary, the free boundary. It's similar to what we had before in last time. It's the normal derivative of u, and I put this epsilon factor because it's not going to change very much. And here is the velocity. Oh, I think I have here, yeah. Okay, so the velocity, and the velocity also, if you think of this representation here for the boundary, then the velocity is the time derivative divided by the gradient in the space. So this is a velocity. This is a x derivative of f epsilon. So the velocity is equal to this, and I can substitute from here this from the first equation, so I get just pu, epsilon pu. Because that's the problem that we have, and we want to see what happens when epsilon goes to 0. In fact, what we really want to see is how to control the thing from the top, which I'll come to it in a few minutes. Now, initially, in each step of this process, we assume that we have something which is already periodic. So the initial data for the moving boundary is a function of x1 and x1 over epsilon. That's again where the epsilon comes in the initial data, and it comes in this p, which is a coefficient of absorption. Let me tell you what the result of this homogenization is. The function u satisfied some nice conditions except here. What happens is that all these conditions remain the same, but here it becomes averaged. The derivative of u0 with respect to the normal derivative with respect to the flat part, so we average this curve to be the flat part, and we average the little p to be, this is capital P by the way. To be capital P, where capital P is the average little p, which was oscillating, and we average it by the distance of the averaged free boundary. You see, you don't see the free boundary here, but it's still there, and its effect was in averaging the p. And the free boundary satisfies the evolution equation for the free boundary becomes this one. The t derivative of f, there is a square root as you saw it before, and there is a p times u, now it is p times u0. So it's not very surprising, except that we have averaged the p. It's not very surprising. And you can actually solve, one can solve this coupled thing. See, to solve the equation here, you have to know P. To know P, you have to know F. To solve for F, you have to solve this equation f sub t equal to this function times square root. This is what's called, it's a simple hyperbolic equation. But you have to know u0 to solve it. So u0 is coupled to this u0. So it takes some circulatory arguments. One can show there is a solution. But actually, what is not so simple, not so easy at all, is to prove that this, what you expect to be the answer, is in fact the answer. It takes lots of machinery, and see, the final thing is that the solution to our problem minus the u0 in L infinity is less than epsilon. The free boundary minus this f tilde here in L infinity is less than epsilon. But to do these things, we have to do some other intermediate steps. In particular, we have to introduce these correcting terms, which is a function of x1. This is x1 should be here. And then comma, x1 comma. This is x over epsilon and y and t. And this is x1 again. And u1 as a function of c and t is a linear combination of the derivative of u0. And these functions, n1 and n2, they solve their own partial differential system in the variable c and t, which I will not write here. This is an intermediate step that is needed in order to get the final conclusions. So this work it's with Behu. It will appear in the Journal of Differential Equations. Now I want to go back to the control problem. And so let's take a diffusion equation which is time dependent. So the heat equation, and let's put here the flux, because that's what we are really given. We're giving a flux g, and the variable g is just not arbitrary. There are limitations. It's always non-negative, but it cannot be bigger than some constant k. There's our mechanical limitations. And the total integral of g, say, is bounded by m. The amount of total flux that we want to put in, we know to begin with that we are not going to put more than a certain amount because we don't want it to be too thick. Okay, so we are going to give, g is going to be a control function. That means for every g, we are going to try to see what it does for us in terms of the growing of the film, and then we will choose the best possible g. So, given g, we solve the problem that I mentioned in the previous transparency, and then we compute the approximate boundary. Remember, this was pretty good approximation up to order epsilon. And this is what we desired boundary. C of x1, x1 over epsilon, and t. C is the level that we want to achieve. And the question is, how to choose g such that the boundary of the film will be as close as possible in the L2 norm to a given shape that we want to achieve. So we want to minimize this function. Of course, we can't expect any explicit solution because I'll give you much simpler problems we cannot solve, with optimize the solution. But we want to get some, well, we want to have a combination of two things. One is some theorems that gives us some understanding of the structure of the optimal solution, and then to use it in order to compute. So assuming that G is optimal, we make a little variation of G, add to G something that still maintains these two conditions. For instance, if you add to G and say epsilon, a delta times another function zeta, then you must, so if you add to G an epsilon zeta, then you must make sure that this function is still between 0 and m and k, and that the integral of G of zeta is less or equal to 0. So that together they'll satisfy the condition. So for such zeta, I'm sorry, this is delta. Delta. So you get a, so what you'll get here is a J of G, if G is optimal, plus delta zeta. This is always bigger than J of G. Okay, you divide by delta and let delta go to 0, and you get some kind of derivative greater or equal to 0, and then you start to work on it, do all kinds of things, that eventually you end up with a condition, optimality condition for G. Now, the optimality condition is a complicated one. If U0, if G was optimal, then and U0 and F tilde were the corresponding solutions, then the optimality condition will say that you can solve another problem in a variable W, which depends on all this data, and this new function will satisfy a certain inequality. You see here the zeta, it comes very implicitly into the condition, and you have somehow to isolate it. Eventually, you would like to get a condition that says that zeta dot something is less or equal to 0 for every zeta. And then the capital phi will be less or equal to 0.
What is the F wiggle?
The what?
Cost function. What is the F wiggle? Is that a...
F tilde was the free boundary that comes with the U0.
Okay.
It told you how the growth of the free boundary is. So I underestimated or overestimated the time it will take me, so I didn't intend to give any details on this control problem. But basically is this: if you want to get a necessary condition, you differentiate this in delta and greater or equal to 0. You get the zeta appears very implicitly here because it's something over there, and when you change into zeta, you change something here in the equation. You get a new U0 and a new F tilde, and everything is very mixed up. But then you have to somehow to all kinds of integration by parts or things like this, or eventually you get some kind of an equality less or equal to 0, where this phi depends on U0, depends on F tilde, depends on G, and you have to solve some system of equations depending on this. And for that system of equations, there is a certain function on the boundary here, and that function is phi, and phi dot zeta is less or equal to 0 for every zeta. Therefore, phi is less or equal to 0. So the condition is that it's very implicit. It says if this is a minimizer, if G is a minimizer and this is a U0 F tilde, you construct a solution to some system and you get a certain function, and the value of the function on the boundary is less or equal to 0. Okay. From this condition, we can draw mathematically a theorem that says that the optimal G, which satisfies this, is either, at each point, is either K or 0. This is on the top here, it's the x1 direction, and the time is between 0 and capital T. So here is a rectangle of x1 and the t-axis up to capital T, and the optimal G is, in some regions it is K, in other regions it is 0, and that's it. This is called the bank control. If the control can be between 0 and K, it chooses to be either at 0 or at K. If you want to bring a pendulum to equilibrium as fast as possible, and you are only allowed a certain amount of force at each time, like this or like this, and the force is between 0 and 1, you always hit it with either 0 or 1. No, between -1 and +1, both ways. So either -1 or +1 in different times, and that's how you bring it as fast as possible to equilibrium. That's a bank principle. So in some cases, this is the kind of control that you get. So it happens the same thing here. It is either K or 0 in some regions. This information is the one that is used for numerical computations. So as we try it by iteration to go from Gn to Gn plus 1, we take a Gn, we create this phi, and we create a see, how do we do that? Yeah, I think yeah. Well, somehow this information is being incorporated into this condition that phi is less or equal to 0 in creating the next one. And let me tell you one curious thing, that this method is extremely fast. If we just try to minimize, each time we choose a G, we minimize, it doesn't minimize, we modify it a little bit and try to minimize, that takes infinite amount of time. But if we use this information that we are only minimizing among functions like this, then it converges much faster. But there is a problem, that sometimes it converges and sometimes it doesn't converge. If it converges, it's very fast. If it doesn't, also very fast. So I'll tell you what we do. Now this is already getting out of rigorous mathematics. I wish I had another transparency. Let's see if I can get something which is fairly clean. Well, let's take this. So this is something about the problems, the difficulties of optimal control. Suppose you want to minimize, to find a G which minimize the following quantity. Since he's taking pictures, I'll better cover this. You look a little neater. So you want to find G such that G minus 1 squared, the integral of dx from 0 to 1 is minimum. But of course we'll take G equal to 1. But I'm going to give you a constraint that G, the G is a non-negative, and maybe let's say less than 2, and the integral of g is equal to 1/2 from 0 to 1. That means you cannot take g equal to 1 all the time because you're going to get out of the bound. So what do? So you're going to make here suppose that g0 is minimum. You change a little epsilon zeta. You differentiate. You use not the Euler equation because it may be on the boundary. You find out that g has to be constant, and it will be something like let's say like 0 and 1 and 0 and 1 say, and the intervals on which it is 1 add up to 1/2. Okay? But this is not the only solution, because I can transpose intervals. I can break this into 2 and move half of it here, and move half of it here, and I can break this into smaller intervals and just jiggle, move them around as I wish. Infinite number of solutions, a continuum of solutions. Now our problem, I am not sure there is a unique solution because it's maybe also infinite number of solutions. It's more complicated to see that there is infinite number, but I'm sure there are lots of them. It's not a sort of a convex problem. Now suppose you want to compute a solution. Okay? So you take something which is close to minimum, and you want to add something nearby. But because there is infinite number of solutions, this is not going to work very well. If you try to approximate it by using the optimality conditions, it's not going to work very well because there's infinite number of solutions. I mean, the variation would will just become insane, because for a split second they'd like to go this way, and then say, well, maybe I'll go this way, or maybe I'll go that way, and it's just going to get very confusing. But let me suggest something else. Suppose that we found, suppose G0 is a minimum, okay? So, you see, let me put it this way. If G0 were a minimum and you want to approximate it by a better one, you can always do it because you can break these intervals a little bit and still get a minimum. So you can make lots of small variations of a minimum and still be in a minimum. So an approximation, is not going to work very well. But suppose that I do the following. If G0 is a minimum, then it minimizes G minus 1 squared. It minimizes G minus 1 squared, right? Let me add to it something. Let me add to it, suppose G0 is a minimum. So it minimizes G minus 1 squared. Let me put here G minus G0 squared with the parameter lambda. It also minimizes this because G equal to G0 makes this equal to 0. Any other minimum of the original problem will not be a minimum for this. Because although it minimizes G minus 1 squared, it will give you something 0 here. So this problem has a unique solution if G0 is a minimum. Okay? Therefore, I would like numerically to change the problem, and once I find an approximation G sub n, once I find G sub n, I'm going to replace this by a new function G sub n, where I will add to this integral, I will add G minus G sub n squared with lambda, and I'll put it here. It's a very simple argument, very simple sort of rationale. by doing so, I have not changed the original value of Gn on this functional, but I am a sort of forcing by unique, because if Gn were a minimum, that will be the only, it'll be the only solution. I am forcing a sort of uniqueness on the problem. It turns out that by doing the approximation and all these optimality conditions, all that stuff on G sub n, we get a much, much better convergence. In fact, it always converges in the cases that we tried, although sometimes it converges slowly, and I'm sure there are cases where it does not converge. But at least we achieve a much better convergence rate with this trick. So, yeah, and numerically, yeah, it's really working like a magic. So I think I'll answer questions, and also if you want to ask me how to start industrial mathematics.
So, I should say the cost function was to make the free boundary
As close as possible
to something that you want.
Yeah, in this particular case, there are lots of things that one can do, but we just want to do a generic thing that eventually, if we have a postdoc working with Motorola, he will be using techniques like this, but the problems will be different, because this is not a problem for semiconductor that you want to make the surface. It is, there are other requirements, I'm sure, but we just took one which is in the ballpark, but it's not necessarily one that.
This is appear somewhere.
This will appear. The asymptotic behavior. I can give you technical reports on this, and also on the fuel tank. And the control thing will appear in Journal of Optimization and Application or something. That's a separate thing. And that's where we, as I said, some things we prove and some things we can compute, but we can't even justify it on a rigorous basis. But it does converge very nicely. We also show that the optimality conditions, and that's important, is not only necessary, but also basically sufficient. So, because you may think, well, maybe the maximality condition also satisfies the same condition. No, it doesn't. It's, in the Euler equation, when you get the derivative, first derivative is 0, it can be minimum or maximum, or neither. Here we show that it's actually a sufficient condition as well as necessary. But we cannot show that we cannot prove that it converges always. So,
thank Mr. Friedman for taking time out from his very busy schedule to visit us. And I think most of you will agree with me that this has been one of the best Porcelli lecture series that we've had. And there are a few of us here that are old enough to have seen them all. I won't mention, there's some of us in the audience, but I won't mention anybody but myself. But, I have enjoyed this. It's been a pleasure to meet Professor Friedman for the first time, and I hope it's not the last time.